Hi there. This video is just to give you a little bit of background about what an exponential function actually is. Now, you've probably seen a lot in the news recently if you've been looking daily at the daily updates, especially at the beginning of the coronavirus crisis. You've seen actually what an exponential curve looks like. It's a curve that starts off nice and slowly, then very quickly it speeds up bit by bit. And exponential graphs are graphs where the x value is actually a power. So for example, we've got the graph of y equals 2 to the power x, or y equals 3 to the power x, or y equals 4 to the power x. These are all exponential graphs, and they all have this general shape. Starts off nice and slow and gets very, very steep very, very quickly. The bigger the base number, i.e. the 2, the 3 or the 4, then the steeper that curve becomes. So for example, if it was y equals 10 to the power x, then that would get very, very steep, very, very quick, and so on. So let me just show this a typical exponential graph. So let's say I want to sketch the graph of y equals 2 to the power x. I've got a table of values here. So if I want to sub in my values of x for minus 1, 0, 1 and 2, if I put minus 1 in first of all, I'm going to get 2 to the power minus 1, which is a half. If I put 0 in next, I'm going to get 2 to the power 0, which is 1. If I put 1 in, I'm going to get 2 to the power 1, which is 2. If I put 2 in, I'm going to get 2 to the power 2, which is 4. So I've got these coordinates here. I've got the point minus 1 half. I've got the point 0, 1. I've got the point 1, 2. And I've got the point 2, 4. So let's plot these then. So minus 1 a half, if I'm going to put my scale in, so let's say that my scale goes like this. Let's say that this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, minus 5, minus 1, minus 2, minus 3, minus 4. So the first point I want to plot is minus 1 a half. Now minus 1 a half is going to be here. Zero 1 is here. 1, 2 is here, and already you can see that's really picking up speed. 2, 4 is here. So this graph looks something like this. Apologies for my dodgy graph drawing here. So that's a graph of y equals 2 to the power x. Let's say I now want to draw the graph on the same sheet here. Let's say I want to draw the graph of y equals 3 to the power x, and I'll do this in red. I'll borrow the same table, and this time I'm going to draw the graph of y equals 3 to the power x. So if it's y equals 3 to the power x, put in the same values. If I put minus 1 in, it's going to be 3 to the power minus 1, which is a third. 3 to the power 0 is going to give me 1. 3 to the power 1 is going to give me 3. 3 to the power 2 is going to give me 9. So let's plot these points then. So my points are minus 1 a third, 0, 1, 1, 3, and 29. So minus 1 a third is going to be approximately here. 0, 1 is here. And that's the thing about exponential graphs, they all go through that same point on the y-axis. Because whenever we make our x value 0, from our index laws, anything to the power of 0 is always going to give you 1. So no matter the base number, even if it was the graph of y equals 40 to the power x, 40 to the power x will still go through the y-axis whenever x is 0. And to make x 0, we get 40 to the power 0, which would give you 1. So we've got minus 1 a third, we have 0, 1, we have 1, 3. There's a slight problem with plotting 2, 9. It's far too high up, but you can see the general idea here, that the bigger the base number, the steeper the curve. And that's exactly what was happening with the coronavirus. The coronavirus had what they were calling an R value of 3 when it started. That meant that for every one person that infected, they then infected 3 other people. So it was increasing by a factor of 3 every single time. So what that really happens here is, that was, if we didn't put in the social distancing measures that were put in to slow the spread, then this red graph would have happened, and it would have kept going and going and going. And the amount of casualties that we've had across the country would have been a lot more than we have just now. Fortunately, yet unfortunately for those that have died. But very interestingly, in terms of mathematics, a real life example of higher mathematics in action is the work that scientists and mathematicians have been using just now to analyse the graph and the spread of the spread of the disease in terms of its exponential properties, in order to bring that down. And I think if you look at the news recently, we seem to be past the peak, and hopefully we're on the way down now. So that's just a quick background into what exponential graphs are.